Hey all, welcome back to another round of chemistry notes. In this video, we are going to talk about bond polarity and molecular polarity. So before we get into that, just a quick definition of polarity. It has to do with how equal the distribution of electrons are in a bond or in a molecule. So if all of the electrons are at one end of the bond or one end of the molecule, that is polar. And if the electrons are all spread out equally, that is nonpolar. So, starting with nonpolar, like I just said, the bonding electrons are shared equally or evenly by the bonded atoms. This can only happen if the electronegativity difference between those atoms is very, very small. So the number we give that is like 0, as in literally no difference in electronegativity, to 0.4. This is just sort of a ballpark number. This is not a thing that you're going to end up using very often. But for very small differences in electronegativity, like almost the same atom or the same atom, that'll be nonpolar because they share pretty equally. This is most commonly seen in diatomic molecules. So remember Brinkelhoff, if you have bromine bonded to bromine, these are the same atoms, so they're going to have the exact same strength, the exact same pull on the electrons, and they're going to share these electrons completely equally. So any diatomic molecule, because that's two of the same atom, or any CH bond. This is the other super common nonpolar bond that you will see. So just kind of put it in your brain that a CH bond is nonpolar, always and forever. Electrons shared equally, no difference. Polar covalent bonds, the bonding electrons are shared unequally by the bonded atoms. The electronegativity difference between the atoms is moderate. You may have expected this to be a large difference, but it's not that different because they're still sharing. They're pretty close together in strength. One is just a little stronger than the other, just a little. So we give this electronegativity differences of 0.4 to 2. And again, this is sort of like a rough ballpark idea. So since one will be a little bit stronger than the other, the atom with the greater electronegativity, the stronger atom, is going to have the greater electron density. What this means is that the atom that is better at pulling on electrons will have more electrons around it because it is pulling on them more. Polar covalent bonds have something called a dipole. Right? We can split this up, di meaning two, and pole meaning sort of ends, right? Like the Earth has poles. There's the North Pole and the South Pole, and there are two opposite ends. A dipole is two ends of a bond or two ends of a molecule that have partial charges. So there's going to be a partial positive charge on the atom with less electron density. So remember, electrons are negative, so something with fewer electrons is going to be less negative or more positive. Not completely positive, it's not getting its electrons stolen, they're just sort of shifting away from it a little bit. So that's a partial positive where there are fewer electrons, which we call less electron density, and there will therefore be a partial negative charge on the atom with the greater electron density. So there are two ways to represent a dipole. You can represent it with an arrow or with deltas, which looks like this. So if you're going to draw an arrow, you point it at the negative element, the more electronegative element, and then on the more positive one, you draw a crossbar to make it a positive. So over here, fluorine is more negative. It has a higher electronegativity, so there are two electrons in here making up this bond, but the fact that there is a dipole, shown by this arrow, means fluorine is a little more negative. These electrons are just kind of hanging out with fluorine a little bit more. Still in the middle, still shared, but fluorine is taking like a little more than its fair share. Again, you can draw that with deltas as well. So a delta shows that it's a partial charge. It's not an ion, This is not a hydrogen that lost an electron and a fluorine that gained one. These are not full charges because they're still sharing. We still have the 2 electrons in the middle that both of them get to use, but again, they're just a little closer to the fluorine. So the hydrogen is a little more positive because it's missing a bit of the electrons, and the fluorine is a little more negative because it's got a little more of the electrons. So then as that difference gets even bigger, right? We had our nonpolar, which is basically no electronegativity difference. Then we had polar, which is like a moderate difference. Then we have ionic bonds, and this is when bonding electrons are straight up transferred between the bonded atoms because the electronegativity difference is very large, right? So it's sort of a gradient, sort of a spectrum. You start with a nonpolar covalent bond, and this blue sort of oval shape represents where you're going to find the electrons. It represents the electron density. So for a nonpolar covalent bond, you have pretty much the exact electron density around each nucleus. This is a nucleus, this is a nucleus, and it's pretty even. You've got the electrons the same amount everywhere. And then as we move from nonpolar to polar, this nucleus is becoming more electronegative as compared to this nucleus. So here in our polar covalent bond, we have a more electronegative nucleus, maybe something like fluorine, pulling a little bit harder on those electrons. And over here we have something less electronegative, like that hydrogen, that can't pull quite as hard on them. They're both nonmetals. They have similar electronegativities, but fluorine's just a little stronger. So the electrons are hanging out a little bit more over here. This is becoming a negative end. This is becoming a more positive end. And then this keeps getting even stronger. So this would be like fluorine and fluorine, completely evenly matched, even distribution. Down here we've got hydrogen and fluorine, similar, but not the same thing. And then over here, this would be like sodium and fluorine. Sodium is a very weak nucleus. It's got a very low electronegativity. Very low, right? It's a metal. And then fluorine is the most electronegative element on the table. It's got a very strong, very high electronegativity. So here, they're not sharing anymore. Here they were sharing, Here, fluorine is so much stronger than sodium, it's not sharing anymore. It said, these are my electrons, I'm going to keep them. And that's when you stop having a partial charge, represented by this delta. Now it's a full-on charge. This is positive and this is negative, because electrons have actually moved from one to the other. These are shared, these are transferred. So in a way, ionic and covalent bondings are similar. They're kind of a similar process, but ionic bonding is the extreme version. The difference is so strong that it just takes the electrons instead of selfish sharing. So again, this is your 0 to 0.4 difference in electronegativity. This is your 0.4 to 2 difference in electronegativity. And this is anything greater than 2 difference in electronegativity. And those values come from this table here. This is how you can calculate your differences in electronegativity. You're not going to get this table on the test. I do not expect you to memorize this table. This table is here to sort of get you used to the idea of polar versus nonpolar versus ionic sort of patterns. But you don't need to memorize these values. At no point will you be asked to return these values. You don't need to memorize them. We are going to practice with them though. So we've got several different types of bonds, a place to predict your bond type, a place to write the actual difference in electronegativity, and then a place to write the actual bond type. So one more time, very small, teeny tiny differences are nonpolar. Moderate differences are polar. Very large differences are ionic. So I'm going to let you go ahead and fill in your own predicted bond type because everyone is probably going to predict these differently. So take a second, pause the video, go through, predict your bond type. I am not going to fill this column in with you because you're making your own predictions. Once you have those filled in, unpause the video and we'll do the rest together. Okay, now that you've got your predicted type filled in, let's go ahead and do our difference in electronegativity. This is a capital delta and it means change or difference. So to do this, you'll find the electronegativity for boron. You'll go to your table, find boron. It's 2.04. You will find fluorine, which is 3.98. Do a little subtraction. When you plug that into your calculator is going to say negative 1.94 because the big thing comes after. For our purposes, you can just go ahead and do absolute value. So this is going to give you 1.94. I think I said 98 a second ago. It should be 94. This number doesn't have a very real application. There are no units for this number. It's just sort of to give us an idea of how different this bond is. And actually, it's pretty close to being considered ionic. This is almost big enough to be ionic. Ionic is anything bigger than 2, but it is 2 nonmetals, which we've been learning for a large portion of the year. 2 nonmetals should be covalent, and it is covalent. It's a pretty large covalent difference, which means this is polar. This is a polar covalent bond. The fluorine has a larger portion of the electrons. It's got a slightly negative partial charge. Boron has a smaller portion of the electrons, so it has a partial positive charge. Okay, on to the next one. We have silicon and fluorine. If you look on your table of electronegativity values and do some subtraction, silicon is 1.90. And fluorine, again, is 3.98. And when you do that subtraction, you're going to get 2.08. And here is why I don't want you to worry too much about the exact electronegativity values. This number, 2.08, is greater than 2. So this column right here tells us this should be ionic. But silicon is a nonmetal, and fluorine is a nonmetal. So that tells us it should be covalent. And it is. It's polar covalent. It's very, very polar, but it is polar covalent. So these numbers are just kind of guidelines to help you sort of learn the different types of bonds, but please don't think this is hard and fast. Anything greater than 2 is going to be ionic because clearly that's not the case. This is more of a pattern thing than a math thing. So this is a very, very polar covalent bond. Fluorine has a partial negative charge. Silicon has a partial positive charge. Remember, fluorine is the most electronegative element on the table. So most things forming a bond with fluorine are going to be super duper polar, bordering on ionic. Next we have beryllium and boron. When you do this subtraction to find their difference in electronegativity values, you get 0.47. So you would probably expect this bond to be ionic because beryllium is a metal and boron is a nonmetal. But this is another one of those awkward cases where beryllium is kind of a weird metal and it will sometimes, on occasion, rarely, form covalent compounds. It only happens with a couple of different types of elements. We did actually see it in the last video. Maybe you caught it, maybe you didn't. Beryllium to boron is polar covalent. All right, that's it for our sort of weird ones. Everything else follows the rules. Next we have carbon and hydrogen, which we said actually in the notes was going to be a nonpolar bond. It's one you can always count on to be nonpolar. When we do our subtraction, carbon is 2.55, hydrogen is 2.2. So subtracting those, you get 0.35. which is less than 0.4. That is going to be nonpolar covalent. You don't have to say covalent every time. That's probably the last time I'll write it. Nonpolar covalent. Next, we have carbon and nitrogen. Carbon, again, is 2.55. Nitrogen is 3.04. When you subtract those, you're going to get 0.49. That's going to end you up with a polar covalent bond. Next, we have silicon and phosphorus. Subtracting those out, 0.29 gives you a nonpolar bond. So in this case, you may have expected it to be polar because they're two nonmetals, but they're not the same nonmetal, and it's not carbon and hydrogen. In this case, they are close enough in electronegativity that it is nonpolar. They do obviously not completely equally share electrons, but fairly equally share their electrons, so it's close enough. And last but not least, we have two hydrogens bonded together. This you should be able to tell just by looking. This is definitely going to be nonpolar because they are the same thing. They should share equally. Difference in electronegativity is 0, so that is going to be nonpolar. These are perfectly even. These are nonpolar. Okay, so obviously this difference in electronegativity thing can be more harmful than helpful. So good news, you are not going to get a table of those values during the test. Instead, you're going to be asked to recognize some patterns. So determining bond type without math is actually easier than determining it with math. You need to be able to recognize the most common polar bonds from memory. 3 of the least electronegative nonmetals are boron, hydrogen, and carbon. If you go look on your table of electronegativities, hydrogen is 2.20, boron is 2.04, and carbon is 2.55. So if you go back to your table for a second, hydrogen, when it comes to electronegativity, hydrogen actually kind of belongs right between boron and carbon. So it should sort of be boron and then hydrogen and then carbon. And then it's a big old jump to nitrogen. So these are your least electronegative. And then it jumps up to hydrogen, oxygen, fluorine, and chlorine. These are your highest electronegativity nonmetals. So if you have an element from the left and an element from the right, that's going to be a big difference between the two. And a big difference means you're going to have a polar covalent bond. So if I say you have a carbon-fluorine bond, without looking at your table of electronegativity values, you should be able to say, oh, carbon is low electronegativity, fluorine is high. That's going to be a polar bond for sure. All right, so let's go ahead and practice that without the math. We are going to identify whether each of these is polar, nonpolar, or ionic. All right, carbon, hydrogen. This is one that you should just recognize off the bat. It's one of your special ones. This is going to be nonpolar for sure. These are two very low electronegativity elements, really close together, and we calculated it in the last set of examples that it's definitely nonpolar. Fluorine and fluorine, both very electronegative, but the exact same electronegativity. So this is also going to be nonpolar. Carbon and oxygen. This is a very low electronegativity element. This is a very high electronegativity element. So this is going to be polar. And if we wanted to draw our dipole, we know that oxygen is more electronegative. It'll be more negative. Carbon is less electronegative, so it will be less negative or more positive. So we can draw this with our deltas, or I personally think the arrow is easier. We can draw our dipole like that. All right, next we have hydrogen and chlorine. Hydrogen is one of our very low electronegativity elements. Chlorine is one of our very high electronegativity elements, so this is going to be polar. And again, since chlorine is more electronegative, it will be more negative, and we can draw our dipole pointing to the right. Next, we have boron and fluorine. Boron was one of our low electronegativity elements. Fluorine is one of our high electronegativity elements. So it's going to be quite a bit more negative over where fluorine is, and this will be a polar bond. And last but not least, carbon is a low electronegativity element. Nitrogen is a high electronegativity element. Therefore, it'll be more positive where carbon is and more negative where nitrogen is, and this will be a polar bond. All right, so let's practice. So let's put this together with what we learned last time. We've got 4 examples here. For each one, we are going to draw the Lewis structures and then identify whether the bonds are polar and draw the dipole if they are polar. All right, our first one is O2. Even without drawing this, we should know that this is nonpolar with an electronegativity difference of 0 because this is the exact same element. So we will follow our steps from before. In this case, we only have 2 atoms, so arranging them is easy. Draw my 2 oxygens, add in their valence electrons to make the Lewis structure. So 1, 2, 3, 4, 5, 6. Same with my other one. 1, 2, 3, 4, 5, 6. And then I can connect any single electrons here. Connect these right here, connect these right here. So that means I'm going to have a double bond here in the middle, redrawing this a little neater. That'll be oxygen, double bonded to an oxygen, and then each atom will still have 2 lone pairs. And then this bond we've said is going to be nonpolar because this oxygen will pull on the electrons just as hard as this electron will. So the electrons will be perfectly balanced in the middle. Neither side will be more positive or more negative. Nonpolar. All right, let's look at our next one. Here we have HCl. We know that hydrogen is one of our low electronegativity elements, and chlorine is one of our high electronegativity elements. But they are both nonmetals, so this is not going to be ionic, it's going to be polar. Polar covalent. We'll save this for last, we'll double check at the end. Go ahead and draw our 2 elements, H and Cl. Hydrogen has 1 valence electron, chlorine has 7. So then we will connect any single electrons to create bonds. Get 1 bond right there. Cleaning this up, that'll be hydrogen, single bonded to chlorine. And then since this is polar, we do need to draw the dipole. Chlorine is more electronegative. It's better at pulling on electrons. So it'll be more negative over on this side next to the chlorine, and it'll be more positive over where the hydrogen is because it doesn't have as many electrons. The electrons are more hanging out on this side of the bond. They're sort of more like this, closer to chlorine. So we can draw this with our deltas, more positive over the hydrogen, more negative over the chlorine, or you can draw the arrow, which should be pointed at the chlorine because that's sort of the way these electrons are scooching over. Then we can double check ourselves by looking up our table of electronegativity values. When you do the electronegativity of chlorine minus the electronegativity of hydrogen, you should get 0.96. So this is larger than 0.4 but smaller than 2, which puts us nicely in that polar covalent range. All right, 2 more examples before you have some practice on your own. All right, here we have BeH2. And since hydrogen is one of our very low electronegativity nonmetals, and beryllium is that special metal this combo right here means that we can have a polar covalent bond between these. So we can arrange our elements, remembering that beryllium goes in the middle because hydrogen cannot be the central atom. Draw one valence electron on each hydrogen, and then beryllium has 2 valence electrons. We'll go ahead and connect our single electrons to form bonds. There we go. So this is going to be our Lewis structure. And while beryllium and hydrogen are close enough in electronegativity to keep this from being ionic, you are not going to have a nonpolar bond with a metal in it. So this is going to be polar covalent. If you wanted to double check that, you can do some subtraction. The electronegativity of beryllium minus the electronegativity of hydrogen is 0.63. So again, squarely in that 0.4 to 2 region. And then last but not least, we have CH2F. So we will put carbon in the middle because we know we can't put hydrogen in the middle, and between carbon and fluorine, carbon is way less electronegative. So we'll put carbon in the center. Just realize this is a typo. This should be H3F. So we'll put carbon in the center and put our 3 hydrogens and 1 fluorine around. Carbon gets 4 valence electrons. Each hydrogen gets 1. And then fluorine has 7. So then our next step is to go in and connect single electrons. We'll form a bond right there, form a bond right here, a bond here, bond here. That'll just about do it. We forgot to check our work on our last one, but we can check here. Each hydrogen has 2 electrons, like it wants to. Carbon has 2, 4, 6, 8, so it's all set. And then fluorine has 2, 4, 6, 8, so it's good. We started with 4 valence from carbon, a total of 3 from hydrogen, and 7 from fluorine. 4 plus 3 plus 7 is 14 electrons. Counting up here, we have 2, 4, 6, 8, 10, 12, 14. So this truly is our Lewis structure, and here we actually have 2 different types of bonds. We have a CH bond and we have a CF bond. Notice that there is no HF bond. These 2 are not bonded together, so we don't have to talk about that one. So we have a CH, which is always going to be nonpolar. It's one you should just memorize. But we also have a CF bond. And this is one that you're going to have to be able to recognize. Carbon is one of your very low electronegativity elements. Fluorine is one of your very high electronegativity elements, which means together they are going to create a polar bond. So then we should draw our dipole. Fluorine is very electronegative. These 2 electrons they are sharing are not actually here and here. They're more sort of down on this end, a little closer to fluorine. Fluorine is hogging the electrons. So to draw our dipole, it'll be more positive at the carbon end and more negative at the fluorine end. So the electronegativity difference for carbon-hydrogen will be 0.35, which again fits into our nonpolar range. And carbon-fluorine is going to be 1.43, which is in your polar range. So you can have both nonpolar and polar bonds within the same molecule because each bond is strictly determined by the 2 atoms on either side of it. These hydrogens are really not affecting our carbon-fluorine bond, nor is this fluorine affecting our carbon-hydrogen bonds. All right, so now you've got a few practice problems on your own. You get a chance to practice drawing your molecules, labeling each type of bond as polar or nonpolar, and then double checking with your electronegativity values. So go ahead and work through those next 4. And when you're ready to check yourselves, the answers are posted on my website. So you can go over there, check the key, make sure you've done them correctly. And when you're ready to move on, go ahead and unpause the video. All right, so hopefully you have become a master at labeling polar versus nonpolar bonds. Now we're going to apply that same concept to entire molecules. Just like there are polar and nonpolar bonds, there are polar and nonpolar molecules. Nonpolar molecules have no net dipole. They might have polar bonds, but as a whole, there's no like slightly negative or slightly positive end to the molecule. There are 2 ways this can happen. Either all the bonds are nonpolar, or all the polar bonds are arranged symmetrically. All the polar bonds are arranged symmetrically and they cancel out. It's like if you had a 4-way tug of war going on, you have the center here, you have someone pulling this way, and someone pulling this way, and someone pulling this way, and someone pulling this way. There's a pull in every direction, but since it's in every direction, it cancels out and this is going to stay put. So this is like your electrons. If they're being pulled this way by something really electronegative, and they're being pulled this way by something, and this way, and every pull is the exact same strength, your electrons are going to stay put, and you will get, overall, no net dipole. There won't be one end of your molecule that's really negative. So for example, that's things like carbon dioxide. Carbon is pretty low electronegativity, and oxygen is pretty high electronegativity, but since you've got a pull of electrons going this way, and a pull of electrons going this way, the electrons are actually not moving anywhere. This pull and this pull cancel each other out because they're the exact same strength. So this is still a polar bond. That doesn't make this bond stop being polar. And this is still a polar bond, but the molecule as a whole doesn't have a positive or negative end. It's perfectly symmetrical. It's perfectly even. There's also something like methane. CH4. That's carbon in the center with 4 hydrogens around it. This is also nonpolar, and it's actually nonpolar, it's super nonpolar, because each of these bonds is a nonpolar bond, and they're arranged symmetrically. So even if they were polar, even if it was CF4, this is also a nonpolar molecule. Even if you have polar bonds, if they all cancel each other out, then the molecule itself will be nonpolar. There is no net dipole here. On the other side of this are polar molecules. A polar molecule does have a net dipole. And again, there are 2 ways to achieve this. Either you have asymmetrical polar bonds, or you've got some lone pairs messing things up, or both. So for example, here is water. So water is 1 oxygen bonded to 2 hydrogens, and it actually also has 2 lone pairs right here. So we've got oxygen pulling the electrons in these bonds, so they're like a little closer to oxygen as it is. And we've got a big clump of electrons up here. So this end of the oxygen has a ton of electrons in it, and it's very negative, versus this end of the water down here does not have as many electrons, and it's more positive. So we can draw our individual little bond dipoles showing that this is a polar bond and this is a polar bond, but you can also draw a single large dipole for the entire molecule, saying this end of my molecule is negative, this end of my molecule is positive. And again, these are partial charges we are talking about. So as far as figuring out whether you're polar whether your molecule is polar or nonpolar. It might sound complicated, but it's actually pretty easy to figure out. If lone pairs are present, the molecule is typically polar. That's kind of all you have to look at. There are exceptions to this. We'll learn about them in the next video. Yeah, there are exceptions to this. We'll learn about them in the next video, but by and large, if you see lone pairs, it is probably a polar molecule. If lone pairs are absent, if you don't have any lone pairs, then you should look at the terminal atoms. If the terminal atoms are all the same, your molecule is probably nonpolar. That was like the CF4 example we saw a minute ago. Carbon in the center with the 4 fluorines around. No lone pairs, and all the terminal atoms are the same, so this is nonpolar. If lone pairs are absent and the terminal atoms are different, then your molecule is probably polar. So this would be like if we swapped a couple of these fluorines out for hydrogens. We had carbon bonded to 3 hydrogens, oops, we ran out of room, and 1 fluorine. There are no lone pairs, but the terminal atoms are not all the same element. We've got this one random fluorine here. This is a polar molecule. It's got a net dipole pointed to the right. It's more negative where the fluorine is, and more positive where the hydrogens are. All right, let's see some examples. Given the Lewis dot structures below, determine whether the molecule has polar bonds and whether the molecule itself is polar or nonpolar. All right, so here we go. Our first one here, does it have polar bonds? We've got nitrogen and hydrogen bonds. We have 3 of those. Notice we're not asked to calculate the difference in electronegativity. This is based strictly on pattern recognition. These are not the same element. It's not bromine and bromine or hydrogen and hydrogen. It's not nitrogen and nitrogen or hydrogen and hydrogen. Nor is it a carbon-hydrogen bond. So for the most part, if it's not carbon-hydrogen and it's not diatomic, if it's neither of those, it's probably going to be polar. So we'll go ahead and draw our dipoles in. We'll say, yes, we have some polar bonds. We have this one right here with a dipole pointed to our more electronegative nitrogen. We have one right here. We have one right here. So then we're asked, is there molecular polarity? Well, yeah, there is. We have polar bonds. They're arranged asymmetrically. We've got a lone pair going on. This molecule is definitely polar. Yes, polar molecule. Then we can draw our molecule dipole. Where is this the most negative? We've got our largest collection of electrons right here. We've got our lone pair right here. Each and every one of our dipoles that we drew is pointing right here. So our overall molecular dipole points sort of to the left. More negative here, more positive here. Negative, positive. All right, let's look at our next one. We have BF3. Notice, remember that boron is one of your doesn't need a full octet elements. So even though it only has 6 bonds, that's all it needs. There are no lone pairs here. So let's start with, are there polar bonds? Well, we have fluorine, which is very electronegative, bonded to boron, which is very not electronegative. So yes, there are polar bonds. There are 3 of them. They point towards the fluorine because that's more electronegative. That's where the electrons are going. So yes, we have polar bonds, but is the molecule polar? Well, we have electrons being pulled really hard in this direction and being pulled really hard in this direction and being pulled really hard in this direction, and therefore not actually going anywhere. They're all being canceled out because these are arranged perfectly symmetrically. So while these bonds are very polar, the molecule itself is nonpolar. This was polar. This is nonpolar. All right, let's take a look at our last one here. We have CH2O. First, do we have polar bonds? Well, not all of them, but yes, we do have some. Carbon is not very electronegative, and these bonds to hydrogen, these are nonpolar. This is a nonpolar bond, and this is a nonpolar bond. However, oxygen is very electronegative. It's really going to pull really hard on these electrons, and this bond right here, this is a polar bond. These electrons are scooching over towards oxygen. So yes, there are polar bonds. And then as far as molecular polarity, these lone pairs on this oxygen don't necessarily mean anything, right? We had lone pairs on our fluorines here, but they didn't affect anything because they were everywhere. When we talk about looking for lone pairs, you want to look for lone pairs on your central atom. Carbon does not have any lone pairs, but its terminal atoms are not all the same. We've got two hydrogens over here, not really pulling too hard on those electrons, and we've got this oxygen over here pulling really hard on those electrons, and this is going to make it a polar molecule. The terminal atoms are asymmetrical, meaning they're not the same all around that central atom. So we are going to have a net dipole on our molecule. It's more positive over here. It's more negative over here. Or if we wanted to draw our arrow, it would be positive on the left, negative on the right. All right, at this point, you've got some practice. On the next page in your book, you have 9 different compounds, even though the numbering is a little weird, that you can draw Lewis structures for, identify bond polarity, and then take it one step farther and identify molecular polarity. And just like always, this key is posted on my website, so once you've had a chance to work through these and actually do it yourself, then you can go look at the key on my website, check your work, and see how you did. And once you've done that, hopefully you're feeling good and you can move on to the next video, work on some quests, work on some test review, whatever you are up to. As always, good luck and happy studying.